Good morning, good afternoon, everyone. My name is Bharadwaj, and today I will present my research on policy based sniffing and attack detection in industrial and hospital IoT environments. In this project, I have developed a distributed Raspberry Pi based wireless monitoring solution that provides proactive detection of sniffing attacks across multiple wireless protocols. This research aims to address critical security gaps in IoT environments. Let's begin by understanding the problem statement. The Internet of Things or IoT is rapidly transforming industries like healthcare and manufacturing. However, this unprecedented connectivity comes with its challenge. For example, devices such as patient monitors or industrial control systems are vulnerable to passive sniffing attacks. These attacks compromise data confidentiality by intercepting sensitive information about without detection. Uh, Also, these IoT devices communicate to diverse protocols like Wi-Fi, Bluetooth, and Zigbee. These introduce complex network architectures at the same time. Uh, mul- Multiple potential attack surfaces are also included. The devices to be secured are patient monitoring systems, Internet of Medical Things, and industrial automation and control systems. Alternatively, industrial IoT. The main challenge is that the traditional security measures focus on active threats and often fail to address subtle passive reconnaissance. Therefore, detecting these threats early and effectively is crucial. This leads us to the focus of my research, proactive threat detection using a multi-protocol monitoring framework. Let's now look at the hypothesis that drives this research. My hypothesis is that a distributed network of Raspberry Pi sensors operating in prometheus mode and strategically deployed in environments like hospitals or industrial facilities can effectively detect passive sniffing attacks across Wi-Fi, Bluetooth, and Zigbee protocols. The framework achieves this through seam-like functionality, which correlates traffic patterns and identifies potential reconnaissance activities. It also uses policy-based detection mechanisms to customize the detection for specific operational environments. Now, let's uh, let's explore the methodology used to test this hypothesis. I designed a framework with four key components. First, a distributed sensor network of Raspberry Pi devices was deployed to monitor wireless traffic across multiple protocols. Second, the centralized analysis was performed to aggregate and process data in real time. Third, the policy based actions were implemented to set customizable rules and thresholds for attack detection. Finally, the system supports multiple protocols, making it adaptable to Wi-Fi, Bluetooth, and Zigbee environments. This experimental setup I used to test this methodology is described next. The experiment was conducted in a controlled small-scale hospital environment. The setup included Raspberry Pi devices equipped with Wi-Fi and Bluetooth sniffing capabilities. These sensors are strategically placed throughout the premises to provide comprehensive coverage. These sensors like sniff the data in the wireless space, uh, basically the Wi-Fi frames and Bluetooth frames, and send them to a central processor where all this data is processed and events are correlated and alerts are raised based on the policy set. Each sensor has the following hardware. Basically, the Raspberry Pi is a uh, sensor is a main component of this sensor, uh, and there are basically four USB sockets. Two of the sockets are used for Wi-Fi. One is for traffic injection, and the other is for uh, sniffing. And Bluetooth. There is another Bluetooth dongle to sniff the Bluetooth frame traffic. Uh, so I have chosen like TP-Link AC1 1300 for Wi-Fi dongles, where its bandwidth is about 1300 Mbps. So one is run in normal mode. This is basically used to enforce policy so that, like for example, you can shut down a rogue hotspot in case it is set in the policy that it is not allowed in that particular area. And the other runs in a promiscuous mode, which basically, you know, like it basically captures all the wireless traffic of Wi-Fi, and similarly for Bluetooth. So I tested, yeah, the data is captured in on 5 different days for a duration of 1 hour, and like approximately 70% of the frames, collected data is Wi-Fi, and 25% is of Bluetooth. The traffic is generated through artificial ingestion of Wi-Fi and IoT, Wi-Fi and Bluetooth communication devices. Now let's explore the results. I tested three common types of Wi-Fi attacks: Evil Twin, Rogue Hotspot, and Deauthentication Flood. For each attack, detection was attempted using two tools: Airborne NG, which is part of Aircrack NG, and Kismet. The results were promising. The detection times ranged from 12.7 to 20.2 seconds, with 100% true positive rates and zero false positives. These results demonstrate that the system is effective in identifying Wi-Fi based reconnaissance activities. Now let's turn to the results of Bluetooth scans. For Bluetooth, the focus was on identifying rogue devices in discovery and paired modes. So one major issue with these sniffing devices is that once they're in passive sniffing mode, it's almost impossible to detect. So basically, one one false signal by these devices, if can be detected, then we can potentially, you know, save our systems from a large attack. That's the reason why detecting a Bluetooth signal in a short duration is significant. The results showed consistent detection of rogue devices with detection times ranging from 16.5 to 25.5 seconds. However, there were challenges with hardware efficiency. For instance, the Bluetooth dongles could only capture frames in a limited frequency band. Despite this, the system was able to detect all active rogue devices during the experiments. The accuracy of Bluetooth detection increases with the duration of the signal produced. Next, I'll discuss the resource utilization of the system during these tests. The system's resource usage was monitored during both normal operations and attack scenarios. The Raspberry Pi nodes exhibited low CPU and memory usage with average CPU spikes of 45% during Wi-Fi attacks and 42.8 during Bluetooth scans. The RAM usage remained under 70% during these attacks. The low resource consumption highlights the system's practicality for real-world deployment in resource-constrained environments. Now, let's summarize the advantages of this framework. The framework has several key benefits. First, it is highly scalable, allowing for deployment across large environments like hospitals or factories. Second, it enables proactive detection of subtle reconnaissance activities before they escalate into major threats. Third, the multi-protocol support makes it versatile and adaptable to various wireless technologies. Also, it supports plug-in plug-out setup so that uh, as per the requirement, we can add on more communication technologies as long as the Raspberry Pi allows to do so. Finally, the use of affordable Raspberry Pi sensors ensures cost effectiveness while AI-driven insights enhance detection accuracy. Despite these strengths, there are some challenges to address. One challenge is the environmental constraints such as interference in high traffic areas. The hardware limitations, particularly for Bluetooth scanning, can also impact the detection efficiencies. Additionally, there is a need to reduce false positives and address privacy concerns associated with monitoring wireless traffic. These challenges uh, also there are privacy challenges in healthcare because there are multiple compliance to be strictly followed. The efficiency and accuracy of this setup is also depends on uh, the strategical placement of all these sensors. So they have to be placed in such a way that it covers all the governed area. Also, uh, they have to be grouped in such a way that the areas can be isolated and different policies can be set for each of these areas. So now let's dive into further work. The future work will focus on testing the framework in high traffic, real world environments to validate scalability and reliability. Efforts will also aim to reduce false positives and improve overall detection accuracy through advanced machine learning models. Other priorities include optimizing the centralized processing framework, integrating privacy preserving mechanisms to comply the compliances and ensuring compliance with regulatory standards. With these enhancements, the framework can become a robust and scalable solution for IoT security. Let's conclude with the key takeaways from this research. In conclusion, this research addresses the critical challenge of detecting sniffing attacks in healthcare and industrial IoT environments. The proposed solution, a distributed network of Raspberry Pi sensors, demonstrated high detection accuracy, low resource consumption, and adaptability across multiple protocols. These achievements position the framework as scalable and cost-effective approach to enhancing IoT security. Thank you for your attention, and I would love to receive your feedback through email or any other channel. Thank you very much.